Well, greetings from the American Segmental Bridge Institute, and welcome to our webinar series for 2025. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute, and if you are not currently following me on LinkedIn and following the American Segmental Bridge Institute, I would encourage you to do so. Hopefully you are here today for Mr. Andrew Mish's presentation on straight and curved precast spliced girders in action. He's going to highlight a number of projects using curved spliced girders. But before we go into the presentation, I want to do a few announcements. Today's presentation is somewhat tied to a recent change at the American Segmental Bridge Institute. The board of directors voted last year to add complex concrete structure technologies to our mission statement. And some people have asked, well, what does that mean? And the answer is it means what we need it to mean. And that is to say, ASBI is here to help provide support to the industry in all things complex concrete, whether it's arches, splice girders, other structure types. And certainly we recognize that we have industry partners like the Precast Pre-Stressed Concrete Institute and the Post-Tensioning Institute that also provide support in this space. And so that just sort of helps recognize that collaboration, some of which we're already doing. Our monthly webinars, hopefully you, when you registered for today's webinar, you did so using the QR code you see on screen. What this will do for you is it allows you to get notified each month of every webinar we're going to do this year. You'll be pre-registered, so you won't have to remember to sign up. You'll already be signed up. You'll get an email when the webinar is created. And in that webinar is an opportunity to click the various calendar types and add an appointment to your calendar. You'll be able to also then go to the ASBI website and see some more information about that webinar to make a sort of decision about whether it's something you want to attend or not. But we certainly believe all of our topics will be worthy of your time and consideration. So again, if you've not done it yet, go ahead and use this QR code to register for the remaining webinars this year. Next month's webinar will be on a Tuesday instead of a Thursday. We're trying to get onto the Wednesday, last Wednesday of the month cadence. We'll start that in the future. We had to move things around for both February and March to meet some people's schedules. But the March webinar will be hosted by Jerry Funtner, will be our presenter. Jerry has a number of years of experience in the industry. I know a lot of people here online probably even know Jerry. He's going to be talking about the construction of the William Halton cast in place segmental bridge, a really interesting project where they used this frame, as you see here, to assist with the erection. So this is a QR code that is unique to that webinar. If that's the only webinar you want to sign up for at this point, use that QR code. Otherwise, use the one that signs you up for all of our webinars. Just a reminder that ASBI does do grouting certification training. That training is required by the PTI ASBI M50 specification for all team leaders. I certainly believe anybody involved in grouted post-tensioning really ought to complete this training. Even designers would learn a lot from this. We're hosting a session in April, on April 7th, here in Austin, Texas. Registration is open on the ASBI website. So if you go into the ASBI website under Learn, you'll find grouting certification and an opportunity to sign up for that training. Just a little plug for a document that ASBI was part of, the National Concrete Bridge Council and AASHTO teamed up a couple years ago and published a document called Resources for Concrete Bridge Design and Construction. This is a really great catalog of everything you might want to know, or at least find the resources for concrete bridge design and construction. And it includes not just resources like specifications and manuals, but it also includes training, both webinar and online, online training and in-person training, certification programs like ASBI's grouting certification. A really great one-stop shop. The QR code on screen will take you to the AASHTO bookstore. You do have to create an account through the AASHTO bookstore, but the publication is a free download as a PDF, and great resource for the industry, I believe. So some quick instructions on our webinar before we get started. Of course, you will miss content if you lose your connection, but if you do, just use the link you were provided to log back in. We will be issuing certificates for professional development hours for those who stay with us through the webinar. There is a minimum time requirement for us to be able to issue a certificate. So please, if you have to exit, please come back in promptly. If you give us about a week to get those certificates to you, you'll get an email link to where those to get your certificate. And then we're going to do Q&A at the end of the presentation, but that doesn't mean you need to hold your questions. You can go ahead in the GoToWebinar dialog. There's a little pull down that says questions. You can type in your questions as we go. Our Q&A moderator, who I'll introduce here in a minute, will collect those questions and then do a moderated Q&A session at the end with our speaker. If you're on a mobile device, you also have that opportunity. There's a little question mark. You hit that little icon, and you'll be able to type in your question there as well. I mentioned our Q&A moderator is going to be Mr. Wade Bonzen with GM2 Associates. He's currently the ASBI Construction Practices Workgroup Chair, and we appreciate Wade being here today to help us to lead us through the Q&A session. Our presenter today is Mr. Andy Mish with Modjeski and Masters. Andy's a project manager with M&M and a complex concrete bridge practice lead for Modjeski and Masters. He's worked in the field of structural engineering with focus in bridge design, construction, and fabrication since 2002, with more than 20 years experience in design and construction and fabrication of precast, pre-stressed, and post-tension concrete bridges. Throughout his career, he has provided design engineering, precast engineering, construction engineering, lots of services in the bridge design and construction industry. And I will mention he's the past chair of the Precast Pre-Stressed Concrete Institute's post-tension bridges subcommittee that ASBI has had the pleasure of doing a lot of work with to help create more resources available in this space. And so with that, I'm going to do my duty and step over here and make Mr. Mish the presenter. And Andy then will go through his presentation. And again, go ahead and provide questions as we go. I have to add, yes, sorry about that. As we go, and then Wade will lead us in a moderated Q&A. If we run long and you need to go, that's fine. That won't hurt you on your professional development hours, but we do like to handle as many questions as we can. So we'll try to answer as many of your questions. So with that, I'm going to turn over to Andy.
All right, thanks, Greg. Are you seeing my screen?
We are seeing your screen and we're hearing you just fine. So I'll go on mute and the floor is yours.
All righty. Well, thank you, Greg, and thank you to ASBI for allowing me to give this presentation. As Greg mentioned, with the expanded scope of ASBI's mission, for those of you who are lucky enough to attend the previous convention in November, there was a few presentations, then a panel discussion on spliced girders that I was lucky enough to participate in. So I'm really excited for this additional charge that ASBI's given us, and looking forward to the future and to see what that brings. So today we're going to be talking about a couple of different case studies using spliced girders, one straight and one curved. And we're going to start out with a project over the Gulf Intracoastal Waterway Bridge at Sergeant Beach, Texas. This is a spliced bulb T girder bridge, straight girders, spanning over the Gulf Intercoastal Waterway. So where is Sargent Beach? Well, it's about 80 miles south of Houston. It's a small residential community right there on the coast. And in order to access their homes, they've got to somehow get over the Gulf Intercoastal Waterway, which, if you don't know, is essentially a major shipping highway. So there's lots and lots of shipping and barge traffic that goes on. So the previous bridge was actually a floating swing bridge. So the residents of this community would sometimes have to wait on either side of the bridge as shipping traffic moved through, upwards of 20 to 30 minutes until the bridge could close again and allow flow of traffic. So TxDOT decided to replace this bridge with a permanent structure that could provide the required navigation clearance, 73 vertical feet and a 225-foot wide navigation channel. So the structure is owned by TxDOT. Modjeski and Masters was the EOR of actually value engineering of the structure. We'll get into that a little bit later. And the precaster was Bear Concrete and the contractor was Austin Bridge Company. So as the VE EOR, we were actually approached by Bear Concrete, the precaster, about this project to help them with their ability to produce some of these pieces. So they were concerned that the initial precast option design, their equipment would not be able to handle some of the large, heavy pieces. So they approached us to look at some alternate solutions that would allow them to actually bid the project. So the main components that we looked at were substructure and superstructure. So the initial design had cast in place bent caps. However, precast alternates were allowed, but we couldn't just do a one-for-one swap. The initial design called for cast in place caps that would weigh 245 tons apiece, or almost 500,000 pounds. And so the precaster did not have the ability to pick or ship those pieces. The other condition, because they were mildly reinforced and were in a coastal environment, was there was a requirement for either stainless, chromium, or galvanized rebar in all of the substructure. So working with Bear Concrete and what their capabilities were, we decided to pre-tension the caps to provide pre-compression and control cracking. And doing a durability study with some slightly increased cover, we determined that we could use black pre-stressing steel and black carbon steel rebar and achieve the same service life and durability for the course of the structure. We were also able to reduce the weight of the pieces by about 50%, making them the heaviest ones 250,000 pounds, which the precaster could handle and haul to the job site. Now, one of the important things when you're dealing with precast is how are you going to connect the pieces in the field? So that was something that we looked at very closely. We determined that we did not need a full moment connection between the cap and the column at the top of the column. So the connection that we came up with used 2 corrugated pipe voids in the precast cap and some projecting rebar spirals coming out of the top of the column. And so we were able to thread the cap over the column and then cast that back with full concrete. So it's not a grouted connection, it's actually a concrete connection. And the reason that we like this type of connection is that you only have 2 connections to align between the precast and what's done in the field, as opposed to 20 to 30 to 40 individual rebars if you're just projecting individual bars and trying to connect those with individual sleeves in the cap. If one of those is off, you're going to have major problems during erection. So working with the precaster and the contractor, we used this concept, which we've used on other substructure projects in the state of Texas, and it worked really very well, and the contractor feedback was very positive. Now, in designing the cap and the connection, what we determined was that the actual controlling load in the connection was the construction loading. So with spliced girder bridges, the construction staging is very, very important. And at the beginning of the design, you have to have a good idea of how you're going to stage the construction and what those requirements are going to be. So we actually had to design that cap connection to accommodate the out of balance loading of girder erection as the controlling load case for that connection. So each of these pier girders weighs about 280,000 pounds. Based on the constraints of the site, we could only get a single crane in there to erect the pieces. So we had to erect from right to left. So the maximum overturning moment that this connection needed to resist was with the first 2 girders erected, we needed to resist about 5,500 kip feet. And we were able to do that with that corrugated pipe sleeve connection. Now for the superstructure design, again, we worked very closely with the precaster to determine what the constraints were in terms of their ability to lift pieces out of the bed with their traveling cranes and ship these pieces about 200 miles over the road to the job site. So the initial design that was bid, this was a traditional design bid build project, had actually 2 options. So there was a spliced precast girder option, and there was also a segmental option, both fully designed, that the contractors could choose which option they wanted to construct and bid on that option. For the precast option, it used variable depth girders over the piers that varied from 9 feet to 14 feet deep with a curved bottom soffit, but it used a non-standard cross section. So in addition to having very heavy pieces over 155 tons, that Bear Concrete was concerned about their ability to actually ship those to the job site and handle them in their yard, they would have had to purchase unique one-off forms, which would have increased the cost for them to produce all these girders. So in our value engineering design, we worked with Bear and within their limits to maximize the piece weights at 280,000 pounds with a maximum girder depth of 12 foot 6 inches over the piers. In order to do that, we had to increase the post-tensioning slightly from 12 to 15 strand tendons. And we also introduced additional pre-tensioning. So it's combination pre-tension, post-tension structure. Pre-tensioning was used both for controlling temporary stresses during handling and shipment, but also incorporated into the final design. Now, one of the unique constraints of this project was the very limited ability to get up and over the navigation channel and then back down to the ground because that Sergeant Beach is a very thin strip of land. So there's very steep grades coming in and out of the main span, plus 7% coming in and minus 7% going out. So if we did a single drop-in piece over the waterway, we would have had significant cast in place haunch buildups over the top of the girders, over 12 to 14 inches in some cases. So our solution to that was actually to split that central drop-in piece into 2 sections, ship those 2 sections to the job site, and actually post-tension them together in a pre-cambered condition to minimize the amount of haunch placement that was going to be required in the field. The reason we did that was that the contractor was concerned about their forms at the top flange, their side forms, having to hold back all of that concrete load and the forms blowing out while they were casting the deck. In addition to that, for the pier girders, we actually precast some of that haunch concrete with additional reinforcement at the precast plant, again, to minimize the amount of concrete that would need to be placed in the field. So if you can see the picture on the right there, it's a little bit difficult to see, but there's a kind of a light gray strip on the bottom, and that is the thickness of the precast flange, and then the darker gray, about 6 inches of concrete above that, was the additional haunch concrete that was precast prior to shipment. A comparison of the girder sections. So one of the ways we were able to reduce the weight to allow the precaster to use their existing lifting and hauling equipment was to reduce the overall section depth from 14 feet to 12'6". The other major change we made was we determined we did not need as deep of a bottom bulb for the negative moment compression. So over the piers, we only had a 2-foot thick bottom bulb as opposed to a 5-foot thick bottom bulb from the initial design. So that saved a good amount of weight as well. The other thing we did with the RVE design was, instead of having a straight line bottom flange, what we were able to do is actually taper the bottom flange thickness from end to center. Again, helping to minimize weight, but also providing a very sleek aesthetic for those haunch pier girders. So casting at the precast yard, we were able to incorporate, as I mentioned earlier, pre-tensioning to help make the design as efficient as possible. So we designed pre-tensioning both for shipping and handling, but also incorporating into final design to control final concrete stresses, and also for ultimate moment capacity. The picture on the top left there, you can see that 30-inch corrugated pipe sleeve, and then there are pre-stressing strands in the top flange of the cap on either side of that. That corrugated pipe sleeve essentially provides a kind of a continuous spiral shear key for loads transfer between the plug and the cap and down into the column, which allowed us to design that connection for the construction load overturning moment that we talked about earlier. And then in the picture on the right there, you can see the long line setup for one of the end span girders with the pre-tensioning in the bottom for positive moment. To give you an idea of the scale of some of these girders, you can see in the bottom right there, that is one of our drafting technicians in our Austin office, Tanya, visiting the precaster prior to girder shipment. So it's one thing to look at these things on a piece of paper or on your computer screen, but getting up close and personal, they're pretty impressive pieces of concrete, pretty impressive girders. You know, one major consideration as we started the design was, how are we going to get these pieces to the job site? Again, the precaster had certain restrictions and limitations with the hauling equipment that they had available. And one thing we actually needed to work and do with them is actually design a special hauling frame for the precast caps. The reason we had to do that, I'll go back here, is as you can see, we've got a bunch of pre-tensioning up in the top. So if we were to try to support this on a truck from the ends of the cap with all of the pre-tensioning, we were actually overstressing the cap in positive moment along the bottom of the web. So what we actually had to do was design a frame where we could support the cap inboard to avoid excessive cracking during shipment. And that's the frame you see on the right-hand side of the screen there. And the precaster has been able to utilize that for precast substructure on other products. So they've been able to amortize that cost over multiple projects. One of the major concerns that the precaster had was, again, they were over 200 miles away from the project site and hauling these big girders over land. And so they were concerned about clearance issues, which was one of the prime reasons that we decided to narrow the depth or shallow the depth of the pier girders. And we actually don't have a picture of it here, but the controlling situation for them was on the final approach road out to Sargent Beach. There was actually some electrical lines that crossed over the roadway that were very low. And so that was the controlling factor for them in the shipping height that they could handle and actually manage to get to the job site. So shaving off that 1'6" from the total girder depth was really critical for them being able to even bid this project. So once we get everything on site, we have to get it constructed. So in terms of the substructure staging, all of the foundations and columns were cast in place on site. The columns were cast with that projecting spiral reinforcement to provide the connection to the precast caps. The caps were then erected, placed down over the rebar with a 3-inch joint. That joint was then grouted underneath, and then the connection was cast with concrete between the precast cap and the top of column. In terms of the superstructure, we had a staged construction and erection plan as well. What we needed to do was erect both side spans fully, cast the splice between them, and do a first stage of post-tensioning to tie those together, because we could not have any false work in the waterway. We actually needed to erect and support the main span girder directly from the haunched pier girders. The initial concept we talked about with the contractor was erecting with cranes on barges. However, after further discussion, we decided that it was really feasible to actually do a strand jacking lift system. And so we worked with Fresnay Heavy Lifting in order to design that system. In addition to the main span, we obviously had to construct the spiral ramps. The contractor is able to proceed with both of those operations at the same time. However, there were some considerations. They needed to leave access for delivery of materials because it was a very tight job site, so they could not complete the ramp all the way. And the other thing that we needed to do was leave that last ramp span open so that we could have post-tensioning jack access in order to post-tension all of the tendons in the girders, both the first stage and second stage post-tensioning. So here we see one of the pier girders being delivered to the job site. And as you can see, with the tight site conditions, coordinating with the contractor for that access and timing of the construction of the ramp bridge was critical to actually get girders delivered and erected on site. Because of the site constraints, we actually only had the ability to use a single crane to erect the end span and pier girders. So we had to deliver those pier girders underneath the end span, and the crane had to swing around 180 degrees to pick it off the truck and then get it up onto the top of pier. The other consideration that we had was due to the significant grade, the pier girder actually had to be erected at a pretty steep grade. So the rigging was very key, that the sling on the right actually had to be about 10 to 12 inches longer than the sling on the left in order to get that pier girder at the correct grade and make all the proper erection connections. So another consideration here, as you can see, is we've got a big 280,000 pound teeter-totter. So how are we going to stabilize it? So we actually have an erection connection between the end of the pier girder and the end of the end span girder. That's a bolted connection. And so it's actually the dead load of the end span girder that's stabilizing the pier girder until we can cast the splices and do that first stage post-tensioning. Once we get the first stage post-tensioning complete, we can erect the main span drop-end girders using that strand jack lifting system. We also designed an embedded corbel. So instead of using traditional external strongbacks, we've got embedded corbels in the ends of the drop-end girder and the pier girder, and all of that is used to support the girder during construction and then is cast into the splice. So there's very little additional material required to make that connection. And here we see the completed bridge over the navigation channel. Final, excuse me, the final span length, so it's 300 feet over the channel with 195 foot back spans. And as far as spliced precast girders go, this is, to my knowledge, the longest span using spliced precast where the girders were hauled overland to the job site. There are a couple of bridges that were built, I believe one in Kentucky and one in Florida. I cannot unfortunately remember the names of them right now, but designed by Jansen and Spons with nearly 320 foot spans. But both of those projects had barge access, and so the pieces were actually barged to the job site. So in this instance, everything was able to be hauled and trucked overland like traditional precast. And this gives you a really good idea why these corkscrew ramps were necessary to get up and provide 73 foot clearance and then get back down in that thin strip of land at the beach was just impossible without that innovative ramp system that TxDOT designed. All right, the next project we're going to talk about is State Highway 99 249 interchange in Tomball, Texas. Again, this is spliced precast, but these are curved precast U-girders. So the precast is actually cast on the radius required. In this particular project, it was about 1,000-foot radius using specialized forms. And so it provides a nice curved aesthetic to the structure. We're not cording and kinking the curves. And this technique was first used for a highway bridge in the United States in Colorado back in 2004 for the Ramp K I-270 interchange at I-25. And I was actually the precast engineer at the precast plant that produced those first girders. So it's been 20 years now, and that bridge is performing very well. So the State Highway 249, State Highway 99 interchange in Tomball, Texas, just north of Houston, was construction of new direct connector ramps. And the unique challenge here was actually the site conditions. As you can see, we already have a 3-level traffic pattern, and we're now trying to install ramps over those existing structures at a 4th level, all while maintaining traffic through the site. So the owner was Harris County Toll Road. Modjeski and Masters was the EOR for 2 4-span bridge units. And then we worked with LJA and Costello to design 2 other 2-span curved spliced superstructure units. The precaster was Valley Prestress, and the contractor is Williams Brothers Construction. So the post-tensioned structures were needed on connectors C and connector G. There was a total of 4 spliced units, 2 2-span units, 2 4-span units on a radius of 912 feet with spans up to 271 feet. And this project was the first application of curved spliced precast U-girders in Texas. So in order to construct the project, we had special false work requirements using straddle bents as needed, but also utilizing cantilevered segments and that same embedded corbel system to erect drop-in girders as needed. So the initial design actually considered steel tub girders for longer continuous spans. However, spliced precast was proposed and eventually selected by the Toll Road Authority. And there was a lot of factors in that, including long-term aesthetics, but also corrosion resistance and reduced fracture critical inspections. So here's a plan view of the project layout with connector C and connector G. So you can see the congested site conditions. Also, we're crossing various roadways at at pretty acute angles. So it became very important to determine what the maintenance of traffic requirements were so that we could determine where we could and could not place false work. And we also had to work with the local precast community to again determine how heavy the pieces could be that we could actually have them shipped to the job site. And so once we did that, we could determine our maximum piece lengths and start doing the layout of the whole structure, determining where splice locations were, and figuring out what our construction staging was going to be. And so again, similar to Sergeant Beach, the construction staging in the design is very important in spliced precast girders, whether they're straight or curved. And that's going to vary from job site to job site. With the tight site conditions here, it was very important to understand where we could and could not fit false work, where we could and could not fit cranes, and how long and how big the pieces could be that we could have the precaster get to the job site. So the maximum piece design weight ended up being a little over 300,000 pounds and maximum length of about 120 feet. So we used a combination of construction techniques in order to accommodate the maintenance of traffic requirements. As you can see in the picture on the right, this incorporates about all of them. So we've got a large straddle bent over the existing bridge. We have a typical false work tower directly underneath a splice location where space allows. And then over the frontage road where we could not put a false work tower, we have cantilevered segments that we are then going to erect drop-in segments to hang from those embedded corbels. In addition to understanding where all the false work could and could not be placed, we also needed to consider during the design what size cranes we would need and where they could be placed. So actually during the design process, we developed a concept crane placement plan prior to bid that was available for all the contractors. And it showed one option for construction and provided information on girder delivery location, crane size, counterweights, boom length, crane location and movements at each stage of construction. And then part of the contract plans was that the contractor was required to develop their own erection plan and scheme for construction, which would then be submitted for review and approval for each superstructure unit. So in the development of the plans, we actually showed, as you can see here, specific crane locations and girder delivery locations, as well as all the assumptions that we used so that the contractor could understand what would be required in order to properly bid the work. Now, using this crane placement and erection plan was not a requirement for the contractor, but it did provide them something to look at during the bid phase so that they could properly price the girder erection. So in terms of the precast girder production, we had essentially three basic types of girders. We had what we referred to as an end girder. So the first girder segment at the first abutment. We had the pier girders in the negative moment region over the piers, and then a drop-in girder on the interior spans in the positive moment regions. So because these girders are actually cast on a curve, pre-tensioning them is really very difficult. While it can be done, you have to have a series of horizontal strand deviators all throughout the length of the form, and you're essentially, with your pre-tensioning, cording along the curve. So that analysis gets very complicated and the construction actually gets very complicated. So another way to handle that is to actually precast these as mildly reinforced and then apply post-tensioning in the precast yard for shipping and handling, and then also for incorporation into the final design. And so that is how we typically go about the design of these girders. There have been curved U girders in the state of Washington where they used pre-tensioning, produced by Concrete Technologies. So it can be done, but it is very difficult and does add a significant cost due to the setup that's required at the precast facility. So using the yard post-tensioning can be very beneficial. So typically what we design these pieces for is actually to be cast as mildly reinforced and then removed from the forms as mildly reinforced and then post-tensioned later in the yard. And we apply specific procedures. So for that piece you see on the right-hand side on the bottom there, that is you can see the end anchorage blockouts there for positive moment tendons for handling. Right now that piece is bunked at about the 2/10 points. When that bottom slab post-tensioning is applied, those bunk points are moved out to the end so that we don't overstress the top of the girder in negative moment. So in terms of the precast production, there's specific staging requirements there as well that need to be considered. Because we're casting these as mildly reinforced and then stripping them and getting them out into the storage facility, it actually gives the precaster and the post-tensioner the ability to post-tension these in bulk instead of having to do one at a time each day in the forms. So you can store a number of pieces as mildly reinforced, mobilize your post-tensioner, install the yard post-tensioning, and get 10 pieces done in a day. And that limited number of mobilizations helps control the cost. So girder shipment is very important to consider, particularly for these curved pieces, because if you support them solely at the ends, they'll want to roll over. So you have to consider where the bunking points are going to be at each stage of construction, including shipping and handling. Need to determine if the girders need to be picked from the end once they get to the job site, or if they need to be picked from an interior set of lifters, depending on where cranes can be located. And so we had to deliver some of these girders along the frontage road, or also along State Highway 99 and 200 State Highway 249 existing bridges. And for any girder erection over traffic, that was all done during nighttime closures, and there was a limited number of full weekend closures allowed on the project. These are very heavy pieces, so we do need to use very big, heavy cranes. 2 800-ton cranes were utilized. Due to the curvature, we actually worked with the contractor on their lifting plan and using an offset spreader bar. You can see in the picture in the bottom left there, those large bright yellow plates. So those are actually offset to counteract the girder roll that wants to happen due to the curvature. So the girder can actually be erected on the proper cross slope elevation. And here's a picture of some girder erection in one of the 4-span superstructure units. Again, you can see very tight site conditions. So we've got a straddle bent over the existing highway with one of the straddle bent false work towers being in between the 2 east-west bridges. And then similar on the far side there with one of the tower legs being in between. And then to erect those girders, they were delivered on the bridges with one crane on the far side and one crane there in the median space between the 2 east-west bridges. So to erect the drop-in girders, our initial design utilized typical external strongbacks, and you can see an example of those in the picture there in the bottom right. However, we allowed the option of the contractor to utilize an embedded corbel system, and that's what the contractor elected to use. What that meant for the pieces, though, is that we actually needed to design a large end block to accommodate those embedded corbels. And so that ended up adding a significant amount of weight to some of the pieces. So the precaster had to understand that and be aware of that in terms of handling and shipping. If you'll recall, I mentioned that our design had a maximum piece weight of about 305,000 pounds. Those large end blocks added an additional 15,000 pounds, so the girders jumped up to 320 kips. So pretty significant and definitely needed to be considered with the erection scheme and the ability of the precaster to handle and ship those pieces. And here in the bottom right, you can see what those embedded corbels look like. Just a concrete filled tube steel, a significant amount of reinforcement is designed in that end block to accommodate the construction loads. And then there's a simple bolted connection from the top plate to the bottom plate of the cantilevered girder. And then you can see the installed girders there on the bottom left, with the drop-in girder being supported from the cantilever portion of the pier girder. Now with the curvature of the girders, it becomes very important to use a lid slab. The girders are stiff enough to be shipped and handled in the open condition and erected in the open condition. However, prior to post-tensioning, we install a lid slab to get a closed section and the torsional rigidity that provides. When we're handling the girders in the open condition, we provide a strut at the handling locations so that any out of plane forces don't crack the web or the top flange. But we don't need any internal diaphragms for stability. These girders are really stiff enough on their own to be self-supporting without that. So the lid slab provides torsional rigidity prior to post-tensioning and helps the structures actually resist the warping loads that occur with post-tensioning, and then that also occur when placing the cast in place deck. So depending on the actual specifics of your cross section, when you close these sections up, your torsional rigidity increases by a factor of 50 to 100. So that's very important. If you do not close these up prior to placing the deck, you will most likely get significant torsional cracking and torsional deflection. That lid slab can be designed either using precast panels, or it can be used, with traditional metal deck and cast in place concrete. If you're using cast in place or precast panels, you do have to design a connection between the girder and the lid slab. So when you use precast panels, you need to make sure that you have a connection there. And what we do is we project some reinforcement from the panel and then cast a cast in place strip between the end of the panel and the top of the girder with reinforcement projecting from both to tie those together to get a rigid connection between the panel and the girder. Once that lid slab connection is made, then you can go ahead and post tension, do your final survey of the girders, and then place your deck forms and do your typical cast in place deck as you would on a typical girder structure. All right, and that about covers it for both of these projects. So I'll be happy to take any questions at this time.
Well, thank you, Andy. And we do have a number of questions. And again, we're just bumping up against the top of the hour. If you need to go when we get to the top of the hour, folks, certainly you're welcome to. But we will run just a little bit long to handle some of the questions that have come in. I know there have been a number of questions, so I'll turn it over to Wade Bonson to moderate the Q&A.
All right, very good. Thank you, Greg, and thank you, Andy, for a really interesting presentation. Since we've got a couple of bridges here that we're talking about, I'm going to drop back and ask a few questions about the Sargent Bridge.
Sure.
First question is for the girder segment over the piers, I guess, what do we call that, the pier girder?
Mm-hmm.
Was it possible to apply a counterweight on the opposite side of the pier head or pier girder when installing that girder, I guess, to get the proper grade?
Yeah, that's certainly one option that you could do. So in this particular instance, let me go back and find a good slide here. So in this particular instance, we were able to have false work in the backspan, but no false work in the main span area. So you could actually potentially apply a counterweight. You just would need to, obviously go through the design, make sure that we're looking at all the proper factors of safety. However, in this instance, what we were able to do was just design a simple temporary connection between the backspan girder and the pier girder, and that provided that tie down, and also allowed for the girder to sit at that proper grade with that tie down connection. But there are, infinite number of ways to skin that cat.
Okay, great. For the haunch sections over the piers, could you talk again a little bit about the casting sequence for that? Was the bottom haunched cord a separate pour from the rest of the height of the girder?
Sure, no, so this is all a monolithic pour. So it's all full depth. We do our best to try not to have those sort of horizontal construction joints within the girders themselves. So that was all a monolithic casting.
Okay. The sequence of the girder erection obviously put quite a bit of demand on that bent cap connection because we started with the outside girder and worked our way from right to left, or in one direction. Did you guys look at different sequences for erecting those girders to try to sort of minimize the demands on that connection? And if so, could there have been significant additional savings, either in the bent cap design or the connection design that might have made it worthwhile to perhaps say move the crane over to the other side, or do something different with that girder erection sequence?
Yeah, we did look at that in coordination with the contractor, but we determined that there wasn't enough room to really either get a second crane in there or be able to move the crane. If you can see here, just behind the crane, you see that building structure. Well, that is the bridge operators building for the existing floating swing bridge, and that's just on the other side of the pier. So there was no room to get a second crane in there, and you can't see it here, but I think it was something like 5 feet in front of the column is actually where the navigation channel starts. So the water is right there as well. So this was really the one and only place on this particular job site that we could fit a crane. And so we really were kind of forced into going with that sequence.
Yeah, okay, understood.
Yeah. And in terms of the actual connection itself, the cap needed to be designed for that maximum moment no matter what, because no matter what sequence you erect those girders in, you're still going to have 2 girders on that cantilever portion. So the cap design would not have changed at all. And the connection design is actually pretty cost effective. It's essentially, it's a corrugated steel pipe, and then, I don't remember the exact, but I think it's like, 10 vertical number 9 bars with a spiral, and then some concrete. So it's a relatively cheap connection. So even if you were to change the sequence, there would be a little bit of cost savings in that connection, but it'd be pretty minimal.
I see. Okay, great. Can you go to slide 19? And on slide 19, the question is, the shoring tower on the end span, was it released when the strand jacking occurred in order to prevent any issues with, uplift perhaps at that shoring tower?
Yes, that's a good question. Yes, so we did consider that, and yes, that shoring tower, there was no tie down force there, so that was released. So when you did the, we did erect that center girder, center drop-in girder. There was no additional force or tie down there required, and it was released, so that did not affect the structure. And also during the final stage post tensioning, there was no tie down force there, so the yeah, no additional loading considerations due to any sort of tie down force.
Got it. Okay. And there was a specific question about what was the girder spacing for the Sargent Beach Bridge?
Off the top of my head, it was about 9 feet on center, plus or minus. It's been this project opened to traffic in 2021, so it's been a while since I've looked at the drawings.
Okay. And given that time frame, were the tendons grouted or waxed? I'm assuming based on that time frame, they were probably grouted, correct?
Yeah, they were grouted.
Okay. How about the interchange in Houston? Same?
Got it, yeah.
Yes, those are all grouted. Yep.
That's Texas, baby.
All right. Let's do a few questions about the Houston interchange.
Sure.
A couple of questions came in about inspection of the interiors of those box sections. Is that something that's required by the owners?
Yes. Let me see if I can get a good slide here. So yes, so there is inspection access. If you see a couple of these girders here, there's a big hole in the bottom slab. And so those are the inspection access points for the girder. So the interior of those girders are inspectable. That also means that, let me see if I can find it here. So I mentioned for the embedded corbels, we needed to add a large diaphragm. And so we still needed an access opening to allow for that interior access. So yes, it is required by the owner in this instance because the girders are essentially tall enough to allow that. These are 84-inch deep, 7-foot deep girders. And so we do accommodate for that inspection access in the design.
Got it. Okay, great. Couple questions about the lid slabs. You talked a little bit about having sort of a cast in place connection for the precast lid slabs. Do you have any more details of what that looks like?
I do, unfortunately, just not in this presentation. There's not a slide I can point to, but this is probably the best one. And what we actually do is we project reinforcement from the ends of the panel, and then there's also reinforcement that's projecting from the top of the girder, and then we essentially cast a 6 to 8 inch wide strip of cast in place concrete that encompasses the end of that panel and will then, through that reinforced connection, tie the end of the panel into the girder so that you get a truly closed section that can resist torsion.
And do you have a similar connection like that for the precast deck slab pieces that span between girders?
No, so it's really only required for that lid slab over the U-girder itself. The center panel is really just more of a traditional panel that you'd see on, traditional simple span precast, whether it's either a U-girder or a bulb T. That special connection is really only required for the lid slab that's over the U-girder itself to provide that torsional rigidity of the individual section.
Got it. Okay. And the lid slabs for providing the torsional rigidity, do they run the entire length of the girder, or are they only needed, sort of near the ends or near the middle of the span?
They run the entire length of the girder. If you wanted to dive down that rabbit hole, you could do some analysis and really dial in exactly how many you'd need. And we actually, on a project probably about 12, 15 years ago, did look at that. And what we determined is that you would need about half the number of panels. And so you'd have an 8-foot panel, then an 8-foot opening, then an 8-foot panel, then an 8-foot opening. And you're going to have to cast a cast in place deck anyway. So in addition to providing that torsional rigidity, these also act as formwork for cast in place. So it just ends up making a lot more sense to just run them the full length.
Yeah. So even if you wanted to reduce them, you'd have to kind of checkerboard them because you needed that rigidity across the whole length of that curved girder.
Exactly.
Essentially. Yeah. Okay. Yeah, that makes sense. All right. Can you talk a little bit about lessons learned? What have you guys improved and lessons learned that you've had for these different bridges? I know you've worked on more than just these couple of bridges, but what in general, what kind of lessons learned have you guys come up with?
Yeah, I mean the biggest, I think, lesson learned is really as you get into the design, particularly if you're doing more of a traditional design bid build where you're not going to have direct involvement with a contractor and you're not going to know their means and methods, is really understanding that construction staging and coming up with a plan for how everything is going to get erected and constructed. Because at the various stages with the various different, potentially staged post-tensionings or loadings or girders, being hung from strongbacks or embedded corbels, the structure is constantly changing throughout the whole construction process. And so you really have to have a good, solid understanding of the construction sequencing during the design process. I think that's really the biggest lesson learned. One of the weird little things on Sergeant Beach that was a lesson learned, but maybe not quite as universal, is previous projects that we'd done, we'd always been able to get multiple cranes, and so we could pick pieces from both ends. And so we actually didn't think about, and the contractor didn't think about, the sling lengths when they were erecting the first haunch girder. And so the first one took about, I think, an hour for them to get that at the right grade and be able to make that backspan connection line up. Just because when you have a single crane, you don't have the ability to lift or drop one end of the girder. It's just going to hang where it wants to hang. After erecting that first girder, when we discussed it and then added a couple shackles to increase the sling length on the backspan side, it took them 5 minutes to make that connection.
Yep. Sometimes simple solutions are the best.
Yep.
All right, one more question here. The cross section at those sort of larger diaphragms, this picture here where you're sort of making that cast in place splice connection, is essentially much closer to a kind of a rectangular cross section. Obviously it's not a full rectangle, but it has a much larger area and moment of inertia in terms of the section properties. So when you have post tensioning, obviously you have the P over A component, the axial stress component, and you also have the MC over I component. And with the additional A size there, larger area, and the additional moment of inertia at those locations, do those become controlling sections for the effects of your PT and the sizing of your post-tensioning?
Yeah, that's a good question. And yes, depending on the kind of the nature of the connection and the diaphragm that you may or may not be using, it certainly can affect it. Let me see if I can get a good picture
Because
here.
you're considering longitudinally the whole
Mhm.
section to be pre-stressed, and so you'd be bound
Right.
by the same allowable stresses at
Yes,
all
and
sections.
then so yeah, but if we're looking at the completed bridge here, if I understand correctly, we're talking about the cast in place diaphragm over the pier.
I think it's the piece over near the quarter points in the midspan where you've got
Okay.
the thicker sections.
Yes, with the thicker sections and the end sections. Yes. So yeah, you do have to account for that that change in cross section. The P over A does go down. Now, typically at your typical splice locations, you know, we do our best to align those with kind of the live load inflection points. So those regions typically don't have as high of a stress demand or an ultimate moment demand. Um, so they don't typically control, but in addition, it's cast in place concrete, which may have a lower strength there. The pieces are combination, the precast pieces are combination pre-tension, post-tension. There's no pre-tensioning in the splice. So all of those factors do affect the design. And it really varies from project to project in terms of kind of when those instances control. In this particular bridge, because it was a pretty consistent layout, it didn't control at the splice locations. But because we actually spliced that main span girder and we have the thickened section there at the splice at the maximum moment region, that was something that we did that did control the design of that splice.
Interesting. Okay, great. Well, I think that's going to about do us for questions this afternoon. So, Andy, once again, thank you for a really interesting presentation on a couple of really interesting, very different bridge structures. And Greg, I'll turn it over back to you.
Yeah, thank you. Thank you, Andy, and thank you everybody for hanging with us a little long today, but that's fine. Again, if hopefully you've signed up for the rest of the webinars this year. If you've not, you can go to the ASBI website and find a link for that. A link to the recording, as well as the slides will be put on the ASBI website under our webinars page here in just a few hours. And again, if you give it about a week, you'll get your PDH certificate in the email. So with that, we will sign off. And again, thank you, Andy, and thank you, Wade, for the Q&A. We're closed.
All right, thank you, Greg. Thanks, everyone.